Okay, let's get started. All right, I'll start by sharing my screen. Okay. All right, so let's adjust the lighting conditions a little bit. All right. Okay, for the people who are following remotely, normally we have a camera in this room, but it doesn't seem to function. It has very little added value because the only thing you actually can see on the screen is basically the backs of the heads of people who are present, which may be amazingly interesting, but which you're going to miss out on today. All right, so this is being recorded as usual for online sessions. So if you're interested in the recordings, feel free to drop me an email. Similarly, I will be using slides. I'll provide you with a PDF version of that, but just email me in order to receive that. Okay, that being said, a small introduction about the material. So this is not my slide deck. It's created by Rolf Rabenzeifner, who is at the moment retired and has been developing this slide deck for the past, I don't know, more than 20 years. And basically, I'm allowed to use this. I'm allowed to use this because I followed 10 years ago or something his Train the Trainer program. And that means that in that case, you can actually use his training material. And yeah, that is very nice. One of the things which I need to remind you of, if you receive the PDF document, please don't share it with non-participants. I've signed this in blood. It's part of the agreement when you are allowed to use the training material. So please don't share this. That's what I'm asking you. And that's what Rolf requires for this training thing. Okay, so this will be going through slides, but also hands-on, if you like, or demo programming, depending on your preferences. I'll ask later on. This is in a way the second part of parallel programming. First part was last week. Some of you were present there, some were not. So in a way, it's one training in the sense that it gives you an overview of, let's say, at least the classic ways of doing parallel programming in Fortran, in C, C++, and sort of in Python. And the advantage of following both trainings is that then you have a good idea of how typically parallel programming in HPC is done, and it's easier to choose between either MPI or OpenMP. But it's entirely possible, and there is no problem with following either one of them or both or whatever. Okay, so let's get started. This is a little bit of an overview, and we'll just go through the first chapter. So the question is, what is OpenMP? OpenMP consists of a number of things. One thing is it is a set of declarations, of annotations, which you can insert in your code. Okay, let's backtrack for a second. I'm using the term code, so that means that we're talking programming languages. So which programming languages can you use OpenMP for? That is Fortran, that is C, and that is C++. That's it. Why? Because support for OpenMP is actually built into the respective compilers. So if you look at the documentation for G Fortran, GCC, or G++, whatever, you will see that there is a flag somewhere that's called -f OpenMP, and that enables code generation for multi-threaded programming in that particular programming language. So it's in fact a compiler which takes these directives, this annotation, and which will translate that automatically for you into lots of code under the hood. Somehow you don't have control over this, it works. Magic, easy. So that's one part of OpenMP, and that's actually a very nice thing, because given that it's only directives, that means that it can be compiled, that it can be ignored by the compiler. So basically that means that a well-written OpenMP program, if it only uses directives, or if you fiddle a little bit, and that's just a little bit, is still a valid sequential program. So that's a nice thing. Given that it is directive-based, it also means that you can parallelize your application gradually. You start from a sequential program in your favorite programming language, and you start adding these declarations. You can do that one part of your program at a time. There's no need to say, okay, I'm going all the way. No, just run a profiler on your sequential program. Look where your performance bottleneck is. Which function is most time consuming? Can you parallelize that? If so, do so. You'll already gain quite a lot. So that's a big advantage when you compare that to the approach which you necessarily have to take when you go MPI. The nice thing is you can start from a sequential program and build up gradually. If you go MPI with a sequential program typically start rewriting it from, well, not entirely from scratch, but in large parts from scratch. So that's a big advantage. So if it's so nice, if it's so beautiful, if it's so easy and whatever, no, it's not easy, we'll see that. But if it's so convenient to do that, why would you go MPI anyway? Well, there is one big difference, and that is in the programming model, which we'll talk about in a minute. So this is shared memory programming. That means that each thread has access to some shared memory. Where does that live? Well, that's the RAM of your computer you're running it on. So that means that by definition, by construction, by whatever, OpenMP is restricted to run on a single compute node. MPI runs on as many compute nodes as you want. So basically that means that OpenMP programs are going to scale, if you write them reasonably well, up to a node and then it stops. If you need more performance, if you need more memory, either buy a computer with more RAM, which nowadays is more or less reasonable to do, or switch to MPI. That's the only thing you can do. As I mentioned last week as well, you can combine MPI and OpenMP It's called hybrid programming, and most important scientific codes, for instance in quantum chemistry and so on, will in fact do exactly that. Okay, so that's one part of OpenMP, that's this directive stuff. Then there are two other parts. One is a library, and that has some convenient functions. We'll see a couple of them, and they typically are used to query the system. How many threads have I got? Which is my thread ID for a particular thread? That kind of thing. And also locking. So OpenMP comes with a locking mechanism. That means you have an object, one thread is modifying it, other threads should not touch it upon until completion of that particular interaction with that first thread. We'll not discuss locking. Well, yes, we will discuss locking and why not to do it, why to avoid it. And actually, typically in scientific programming, we don't really need that. That, by the way, locking is one of the reasons why Python is extremely slow and very non-trivial to parallelize in a reasonable way. Because it locks each object, meaning that only a single thread can, under any circumstance, access a particular object, and basically, yeah, that stops that serializes everything implicitly. It's called in Python. It's called the GIL, Global Interpreter Lock, and the unfortunate thing is the global in that abbreviation. There is an attempt at the moment to create something very like OpenMP for Python, but I really wouldn't recommend to use that in production because it's really, really early stages, but it's an interesting development to keep an eye on. So that is definitely something to check out. If you're interested in parallelizing Python and so on, there will be a Python for HPC training first semester next academic year. And I've extended it from 4 hours to 8 hours, so I will probably, for the first time ever, be able to cover half of the material rather than 25% or something. Anyway, so the last part, which I didn't mention yet, is environment variables, and with those you can control the execution of your OpenMP program. For instance, you can say, okay, I want to run this with 10 threads or with 16 threads, whatever. So that's something that you can control at runtime through environment variables, which is very convenient. So those are the three parts of OpenMP, basically. And OpenMP is just MPI as standard, so there is a booklet which is much thinner than the one for MPI. The one for MPI is something like this. The one for OpenMP is something like that. It's also much less well written, with all respect to the standard committee. I mean, the MPI standard is really, really nice. The OpenMP standard is okayish. I mean, yeah, well. One of the reasons why OpenMP is a bit more tricky, you can already guess from what I've been saying, because as I mentioned, there is compiler support for that. Okay, but compilers also, of course, have to stick to the standards of the programming language they're going to compile. A Fortran compiler has to be compliant to the Fortran specifications, similar for C, C++, etc., etc. So if you're going to mess with the compiler, it actually means that you really, really, really have to be aware of all the very subtle semantics of the programming language you're starting to mess with. So that is pretty non-trivial. To give you an example, for those of you who are familiar with Fortran, in Fortran 2008, the block construct was introduced, which is rather nice. It allows you to declare local variables, to, let's say, restrict the scope of variables, which you couldn't do in Fortran previously. Okay, so that's cute, that helps, but it doesn't work with OpenMP because the standards committees can't really agree on the semantics of the block statement in the context of multi-threading, etc., etc. So it does not work. Well, it does work with GCC, with gFortran. It doesn't work with ifort. ifort will tell you, I'm not going to do this. It's not in the specification. Don't even think about it. The gFortran compiler will do something which maybe is correct sometimes, maybe not. I have no idea, but I'm not going to use it. So you have this interaction between standard committees or the lack thereof, and that complicates things a little bit. Okay, one of the things that OpenMP, very modern OpenMP, is also doing is offloading to accelerators. So basically, the data movement between your host memory, so basically what your CPU operates on, and device memory, what your GPU operates on, can actually be done using OpenMP. And that's rather nice. And that means that you can do GPU programming using just OpenMP. And that is possible if you get it to work. Spent a very frustrating afternoon yesterday not getting it to work, but okay, maybe I'll get there at some point. But in theory, it ought to work. Anyway, the data movement does work, but getting something to compute with OpenMP, that's, yeah, well, not working for me. Let's put it that way. Okay, so that's a little bit the scope of OpenMP. Basically, what does that mean? Well, let's talk a little bit about hardware architecture of typical compute nodes. So a typical compute node in a cluster like ours, so the VSC infrastructure, has a motherboard with two CPUs on them. So basically, the CPU is your central processing unit. That's what does the actual work in your computer. If you have a laptop, then typically that has a single CPU. Workstations may have multiple CPUs. Compute node in clusters typically has two. So that basically means that we have to look at the CPU, and the CPU itself also has multiple, let's call it compute units, in technical terms, cores. And of course, if you look at the specs of your laptop, you will see that it may have 2 cores, 4 cores. If you pay a lot of money, it may have 8 cores. And it may tell you that it has more cores. But typically that's sort of lie, because what you typically see reported as the number of cores in your laptop is not the actual physical number of cores, but the number of threads you can run concurrently on your system. Okay. Concurrently means that they're also executing. Because if you look at the number of threads which is executing on a typical laptop, you get something like 10,000. I don't know. I mean, lots. Most of those threads are absolutely doing nothing, just sitting there waiting for someone to activate them so that they can do something if required. But if we're talking compute nodes, then of course the number of active threads is typically what is doing the actual computations you're interested in. So your typical simulation or whatever you're doing. Okay, so each of those cores can in fact, or the manufacturer will tell you, and they're not lying, that it can execute 2 threads at a time. Yes, that's sort of true, but not quite. Because what they can't do concurrently is floating point math. Okay, so basically that means if I'm running 2 threads on a core, one will have to wait for the other to do floating point computations, and that means that they're running in serially, because our code typically is full of floating point computations. So that's why typically on a compute node, we disable this feature and we restrict the execution of a thread, of a core, to running 1 thread, period. No discussion. And that will improve performance. because you generate overhead if you have multiple threads. Well, two threads on the same core, you are going to generate a little bit of overhead, given that you're going to serialize the thing anyway, because floating point unit is not shared, is shared rather, it is not double. Yeah, okay, what's the frigging point? You're just generating overhead. And that is something you see in benchmarks. On your laptop, that is typically not true. Hyperthreading, as that feature is called, is enabled. And that's why, for instance, my laptop would report that it has 16 cores, while actually it has only 8 physical cores, on which indeed you can run 2 threads concurrently as long as they don't do any floating point. And of course, that makes a lot of sense because most desktop applications don't do that much floating point. They do integer. So who cares? It's a good design choice for a general purpose processor. Okay, so basically that means you've got a lot of cores in a CPU. Typically nowadays in compute nodes, you've got 32 or you've got 48 or whatever. You can have up to 64 cores at the moment. I think that's the maximum. CPUs will come out with 96 cores, etc., etc. So that means that in practice, for instance, on Genius, you would have 36 cores. On Wise, you will have 72, and on the tier 1, on Hortense, you would have 128 per compute node. Because those two CPUs are sort of transparent. If I've got two CPUs with 18 cores each, I'll see 36 cores. Easy. So I don't have to take into account that in fact I'm using two CPUs. Well, not quite. We'll see that it makes a difference. But okay, for now, we don't need to worry too much about it. So that's basically the idea. OpenMP goes a little bit beyond that, at least modern OpenMP. It also allows for SIMD instructions. That means factorization. A single core can do multiple operations simultaneously on data. So SIMD means single instruction, multiple data. So a modern CPU core can in fact operate on, let's say, 4 double precision numbers simultaneously. So it can do 4 multiplications of two double precision numbers in one operation. More modern CPUs can do that on 8 double precision numbers. So they have wider vectors, as it's called, and they have 512-bit vectors. Okay, that costs you CPU frequency, but okay, let's not go there. So basically, OpenMP also has a vocabulary to say, well, okay, I want my loops vectorized, and compiler, yes, you can do that. Please feel free to do your thing. So that's basically also important to realize. We'll come back to that somewhere in the afternoon. Okay, so now we're a little bit familiar with the hardware. So what's now the programming model of OpenMP? With some luck, that's somewhere on the next slide. Yeah. Distributed memory, we know. So basically, this is a very this is a little bit of Fortran code. Even if you're not familiar with Fortran, it will be easy to understand. We have two arrays, A and B, and as you can see, they have the same dimensions. So these are 2D arrays. Okay, we're going to loop over those arrays. So we have two do loops, and we compute the elements of B based on the elements of A. So this is basically some stencil computation where you take an element of A and its neighbors, do some computation and assign that to the corresponding element of B. That's basically the idea here. Okay. Okay, the C programmers are getting worried. C++ too. Why are they getting worried? I can also reverse the question, why are the Fortran programmers happy when they look at these do loops? This is just an aside, but useful to check. Yes, loop order. So this loop order is correct. Well, correct for some definition of correct for Fortran, because in Fortran, two-dimensional arrays are stored column-wise. So the index which changes most rapidly is the row index. So that's your inner loop in Fortran. In C, C++, situation is different. Their arrays are stored row-wise typically, and you would like your column index to be the inner loop. So you would exchange the I and the J loop in C, C++. Just something that you need to be aware of. Okay, never mind. So what are we going to do? We are looping, etc., etc. So yeah, nothing much interesting is going on here. So can we parallelize this? The answer is yes, on condition that the iterations are independent. Okay, A doesn't change. I'm never assigning to A, so no problem. Each expression in my do loop actually depends not on any other value of B. If I'm updating Bij, I'm not touching any other value of B. Bij is only changed in one iteration, or in this case, assigned in one iteration. So my loops are independent. Okay, if my loops are independent, there is nothing that says that I cannot do them in parallel, because the order is irrelevant. So I can do them in parallel. Okay, that's very easy. The only thing we need to do is to insert some um, come on, annotation, directive. That's the word I was looking for. I keep on forgetting directive today. I don't know why. Anyway, I just need to insert a directive. The directive I'm inserting is parallel do. And you see this somewhat strange prefix here, exclamation mark $OMP. So that is just a convention. The exclamation mark means that's a comment. That's the thing in Fortran. And the $OMP is convention. That basically means that this is an OpenMP directive. The directive is a parallel. Parallel means, okay, do your thing. I want multiple threads to do whatever is in this block of code. And what I'm going to parallelize is the do loop. So this do loop is going to be parallelized. To be precise, the loop over J is going to be parallelized. So everything between OpenMP parallel do and OpenMP and parallel do is going to be done by multiple threads. And the division of work among these threads, the work is going to be individual iterations of my out and do loop. That's going to be assigned to the threads which are going to execute this particular piece of code. So that's basically the idea. Okay, that was easy. We're done. Yeah, no, not quite, but this is the spirit. In OpenMP up to 3.1, this is actually the main thing you're doing. You're parallelizing for loops. Things get a little more interesting with OpenMP, in fact, already in 3.1, but it wasn't implemented well, wasn't defined that well. But in OpenMP 4, we get tasks, and then things get a little more exciting in a way. But basically, this is the basis of OpenMP. You've got a for loop or a do loop. You parallelize that, you're done. Easy. Okay. All right. So we have a lot of shared memory directives. So what is going to happen? When you start executing an OpenMP application, only one thread is active, and that's your master thread. And that will remain active during the execution of your program. It will only stop as soon as your application terminates. Your main thread is always going on. Okay, And then you have an OMP parallel. And that is going to spawn multiple threads, which are going to execute some of the work, each preferably some part of it, not the same. So that's going to happen. And then you have the parallel end, or the end parallel, and then only the master thread is going to continue. The other threads may or may not keep on existing. That is implementation dependent. As a programmer, you don't really care whether that happens. You don't really influence this. This is up to the OpenMP runtime, whether it keeps a thread of, a pool of threads active or not. And typically, if you have a halfway decent OpenMP runtime, yeah, you'll keep these threads alive, because otherwise creating threads is expensive. You don't want to do that all the time. Okay, so then a single thread is continuing, again, this master thread, and then we can have another parallel region. Again, these threads which were somewhere squirreled away in some pool get reactivated, get work to do, and an end parallel, and so on. And at the end of the day, that is your application. Okay, so let's skip this for now. And let's skip the message passing thing because we did that last time. So this is just by way of comparison what you would actually have to do in MPI. Lots more code, essentially rewriting your application. Right. So basically, why would you want to use OpenMP? So the time which is here is the time you spend as a programmer. So that has nothing to do with execution time. The y-axis is the performance. So the better the performance, the higher up on the scale. Very easy. So basically, as long as your program is scalar, of course, the more effort you spend, the better its performance might be. Hope you know what you're doing. You use a profiler, you optimize, blah, blah, blah. Yeah, you can do that. It takes a while and you will improve a little bit. But of course, that ends at some point. You want to parallelize. So if you want to do that, then with MPI, you spend a lot of time during which you are rewriting your code and nothing happens because it simply doesn't work yet. And only then you get a very nice gain. So that is your typical effort with MPI. OpenMP, you start improving immediately. And you get to some performance, but it will, of course, by construction, by definition, be less than what you get with MPI because you're restricted to a single node. There it ends. With MPI, you can scale to any number of nodes. Well, not quite, but a reasonable number of nodes, depending on how well you program, really a lot of nodes, so that depends. So that's a little bit the difference between OpenMP and MPI. And if you combine the two, you will still gain a little bit, because OpenMP, due to the lack of communication, typically is a little bit more efficient on a single node, but that won't be that much. So yeah, whether you want to go hybrid or not, it depends. It will significantly increase your development effort and the difficulty with which to debug your code. Debugging hybrid is not so nice. So whether you want to go there or not depends. The nice thing is, well, if I would have to, if I'd start to write an application from scratch and I know it needs lots of performance, then I'd probably go MPI and then perhaps add OpenMP later, if it makes sense. Okay, so other motivations for OpenMP. Yeah, well, You have other ways to multi-thread your code. For instance, you can use the pthreads library in C or C++. In C++, in modern C++, you have the algorithm part of the standard template library, and you can set an execution policy. That execution policy can be parallel. And magic, you link with TBB, threading building blocks, and you're done. Your application is parallel. Hooray, easy. Okay, performance is not that good, but okay, you can't have it all. But it works. So that is definitely an option. But then, yeah, that works for C++ because TBB is a C++ library. Don't think of it if you're writing C. Don't even consider it when you're doing Fortran because that is never ever going to work. So yeah, there are some specific options. Another option for C++ again is Sickle, which is really, really nice. It allows you to write parallel code that can run on heterogeneous hardware. Quite cute. It can run on CPUs, it can run on GPUs, it can run on both. Really cool. But again, C++, C++ only. So there it ends. So in that respect, OpenMP is nice because you can use it for C, you can use it for Fortran. Okay. So basically, the question, of course, is how much overhead do you have? Because that's, of course, something you need to consider. That has to do with scaling. And of course, what you hope is that if you have an application that runs in a certain amount of time on a single core, and you use 2 cores, that the wall time, so the time it takes to execute, will be half. Yeah, maybe, maybe not. If you use 4 cores, the wall time is divided by 4. Yeah, maybe, maybe not, likely not. So the question is, how far can you go before things get silly? In the sense that suppose that I have my OpenMP application and I run it on 36 cores and it runs 6 times as fast as single core, then I have a 6 times speed up, which sounds nice, but my parallel efficiency, that is my speed up divided by the number of cores I've got, is not going to be that impressive because that is 6 divided by 36. That's 1 over 6. That is, I don't know, less than 20%, something like 15%ish. Yeah, 16 to 17%. Parallel efficiency, yeah, that's really, really, really crap. So that's not a good way to run that application. It's very inefficient. So typically, OpenMP can have quite some overhead, and that's one of the reasons why it's not that trivial. It's trivial to write, well, no, it's reasonably trivial to write a correct, badly performing OpenMP application. It's not so trivial to write an efficient OpenMP application, which is still working correctly. So that is mostly what we are talking about today and why we have quite a number of constructs. Okay, so simple OpenMP program, in this case in C++, sorry, in C. So basically, where we have the exclamation mark hash OMP, sorry, exclamation mark $OMP thing in Fortran, we have pragma OMP in C and C++. So pragmas in general in C and C++ are in fact advice to the compiler. So those you can use in order to steer how the compiler is dealing with your code. So those are in general compiler directives. And that is what the OMP standard for C and C++ piggybacks on. And it's what directives are supposed to do. They are instructions for the compiler. Generate some code. Do something. That's for the compiler. So this is a very general mechanism in C and C++. So we have to specify OMP in order to tell the compiler, okay, the compiler knows if it sees pragma that it's got something to do. So the something it's got to do is some OpenMP thing. And again, we have parallel and we have for in this case. So notice that the OMP standard is language aware. So where in Fortran you would have parallel do, in C, C++ you have parallel for. Makes a lot of sense. You have a do loop in Fortran, you have a for loop in C, C++. So yeah, pretty straightforward. Also note that in Fortran, an OpenMP directive opens and ends. So we have OMP parallel do, OMP and parallel do. Everything in between is the scope of that particular directive. And that's the way you always do things in Fortran. If you have a do loop, you have an end do. If you have an if, you have an end if, etc., etc. So that's the way it's done in that language, and that's the way that OpenMP also does it in its specification. So in C, C++, we don't have closing things. If we want the for loop to do several things, we have to define a block of code, which we do by curly brackets. Very easy. All of this is the body of your for loop. And basically, the semantics of OpenMP directives in C++ is similar. They are for the next statement or for the next block. So in this particular case, the only thing that's going to happen in parallel is this particular for loop. If there were another statement below that, that would not happen in parallel. If I want that to happen in parallel, no problem. The only thing I need to do is to insert curly brackets here and there, and then everything, the whole block of code in those curly brackets is going to be in the scope of that particular directive, that particular OpenMP directive. So that's nice. The semantics of your language is basically respected in the OpenMP standard for that language. So that's a nice thing. So that makes your life as a Fortran programmer easy because you think in terms of Fortran. It makes your life as a C, C++ programmer easy because you can think in the semantics which you're used to. But yeah, I mentioned that that means that OpenMP guys have to talk to C guys, to C++ guys, to Fortran guys in order to get those standards tuned to one another. So that's interesting, but not my problem. I'm not in any of those standards committees, so that's someone else's problem. Okay, so this is speed up, efficiency, scale up, etc., etc. So for those of you who were at the MPI training, I already explained this. Let's do it again because it's fun. So basically, how do you get a speed up? And that is very often reported as quality measure for your parallelization. Speed up is very easy. You just time the time it takes for your application to run with a single core. So with a single thread, or in MPI terms, with a single process. And then you time how much time it takes with n cores, and then you divide. Easy. And that will be, hopefully, a number larger than 1. If it's less than 1, then you've really written crappy code. So typically, your speedup is an integer, well, not an integer, sorry, floating point value, which is larger than 1. Okay. But I already told you that speedup is deceiving. If I tell you that the speedup of my application is 6, then you may or may not be impressed. Sounds nice, no? I mean, 6 times faster, whoa. But on the other hand, if I need 36 cores in order to get there, then that is way less impressive. So that's why typically when we talk about speed up and scale up and whatever, that we don't mention speed up, but that we look at parallel efficiency. And parallel efficiency is quite simple. Take the speed up, divide it by the number of cores you needed in order to get that speed up, and you're there. And that typically means that your speedup is going to be less than 1. Interestingly, your speedup can actually be larger than 1, which is kind of spooky. But yes, it happens in reality, not much larger than 1. It's not going to be 2 or something, but it might be 1.2, 1.1, 1.2. So that's a little bit spooky, but that has to do with memory management, which is interesting, but beyond the scope of this particular training. Okay, so typically, suppose you're preparing for a tier 1 benchmark, please use parallel efficiency, don't use speedup. The allocation board will start nagging if you use speedups. They will say, okay, we don't care about speedups, we want parallel efficiency. All right, so scale up, actually there are two ways of defining scale up. We have strong scaling and we have weak scaling. So strong scaling is pretty straightforward. You've got your wall time for a number of cores. You want the number of cores, and you hope that the wall time is divided by this by the additional factor. So basically, if I double the number of cores, I hope that the wall time will be divided by 2. So that's strong scaling. Does that happen? No, never ever. Why? Could happen? Well, it can sort of happen, but never quite. So basically, when you think about it, then actually the execution time of your application can be split into 2 parts. One part is the execution time spent in a region of code that you can parallelize. Hooray, hooray. And another part of your application is going to be inherently serial because you can't parallelize it. Okay, that's kind of nice, but what does it mean? It basically means that however many cores I throw at my application, the serial time, the time spent in the serial part of your code, is going to remain constant. Because it's going to run on a single core, regardless of whether I have 125 or 396. It's always going to take that same amount of time. And then, of course, the time spent in the parallel region of your code is going to speed up. That's not a problem. And if you're lucky, indeed, you get perfect scaling and it will be divided by the number of cores you have. But that means that your parallel efficiency by construction is going to peter out at some maximum value. That's just plain mathematics. So there's nothing to do about that. Strong scaling, unfortunately, does not really exist. And that is called Amdahl's law in literature about parallel programming. There is also another type of scaling, and that's weak scaling. And that basically says, okay, I've got a given problem size, and problem size might be the dimensions of a grid I'm processing. It might be the number of data items I'm processing, whatever. Essentially, a quantification of the work I need to do. So if I need a certain time for that, and I double the amount of work, then the time it takes will also double. That's weak scaling. And this is something that is easier to achieve in scientific programming and also something that we are interested in. Because it means that, take a molecular dynamics simulation, if I double the number of particles, okay, not going to happen because things are quadratic, but essentially the wall time is going to go up with a factor of, okay, not 2 in this particular case, again, you would have something quadratic somewhere, but at least something controllable. So that is basically weak scaling, and that is, I won't say easy to achieve, but much easier to achieve than getting very good strong scaling. Okay, so that, by the way, is Gustafson's law about weak scaling. So basically, here you see it computed. So this is the number of processes, and that's the speed at which you're going to get, depending on, for each of the different curves, which fraction of your code is inherently serial or not parallelized. And then you see that even if only 1/1000 of your code is in fact, you can't serialize it, you still see that it falls off pretty rapidly because this is 100. So essentially, you already see a significant difference for only 100 cores. So that's Amdahl's law in action, basically. Okay. So this is a little bit an overview of who is in the standards committee for OpenMP. So you will see a number of household names in HPC, a number of processor vendors. For instance, nowadays NVIDIA is also quite active in the OpenMP standards committee for obvious reasons. So basically, it's a mixture of, on the one hand, operating system developers, on the other hand, hardware developers, compiler makers, academics, etc., etc. Okay, a little bit of history, release history. So as you can see, it all started with one specification. Then they decided, okay, let's make two, one for Fortran, one for C. And then after a while, they decided that that was a bad idea, and they unified the thing back into one specification. And as you can see from the timeline, it started rather early, so a little bit later than MPI, but you can say they're contemporaries in a sense. And you see the evolution. So every couple of years, there is a new iteration of the standard. The last one, as you can see, in 2021, and that's OpenMP 5.2. What is nowadays mostly added is indeed stuff for offloading, for doing computations not on your host device, but rather on devices which are somehow attached to your CPU, like GPUs, like FPGA, blah, 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 all that kind of interesting hardware. So that's basically the idea. We'll mostly be talking about OpenMP 3 and OpenMP 4.5. All right, so this is a little bit of an overview of things that were added. So as you can see, stuff that was added in MPI 4 is support for SIMD and some support for accelerators, mainly data movement. So tasks were introduced earlier in OpenMP 3, but yeah, somewhat underused. They got much more useful with later iterations of OpenMP and especially with later iterations of compilers. Because the task engine, which has to do the scheduling and so on, improved over time. And especially Intel did a very interesting job there with their acquisition of Silk, special task-based programming language extension of C, and then they turned that into TBB, which now you can use with many compilers and have automatic parallelization, for instance, as I mentioned for C++. Okay. And then in 5, you've got some reduction. So again, the task loop, as you can see, is introduced, is going to be improved. And that is basically due to the influence of, for instance, TBB and other programming models which are similar. Okay, so a few books. Nothing very recent, as you can see, like the latest one is 2008. Now, this one here is actually a very good one. So the Introduction to High Performance Computing for Scientists and Engineers by Hager and Verlaine. That is a very good book, and I can recommend it wholeheartedly. You can have it in a Kindle version. It's a very interesting book. So it has a shortish introduction to OpenMP, a shortish introduction to MPI, but it mainly talks about how do I optimize my code for use on high performance computing. So it mostly deals with single node performance and optimization of that before starting to do multi node computing and so on and so on. Georg Hager also gives very good trainings. That was typically part of the PRAISE training program. We also had him over here a couple of years ago. So that's really a very nice training. If you ever see it advertised somewhere, it's definitely worth traveling. It's very good training. Okay, so let's start with the programming model. MPI was shared nothing. MPI is a bunch of processes that run independently and that have to communicate by exchanging messages, hence MPI, message passing interface. So the philosophy of OpenMP is the entire opposite thing. That's a shared memory programming. So each thread in this case, so each independent execution of instructions, line of instructions, can see the complete memory of your application, shared memory. Okay, so that's already quite a different mindset. But of course, there need to be things private for each thread. So there is a mechanism to say, well, okay, this variable will be shared among all threads. These variables will be private to each thread. So each thread has its own copy of that particular variable. That means that if you mess up and you intend a variable to be private, but it happens to be shared, that you are in trouble. You will get race conditions. We'll talk about race conditions later on, but that is something that unfortunately you can have. So in order to avoid race conditions, first get your sharing policy right. I mean, if something is private, declare it as such or you die. So that's one thing. But also you need some synchronization. And that synchronization can be implicit or it can be explicit. We'll talk about synchronization and constructs to control that later on. So basically, threads are in a way independent streams of instructions which are executed. That's the easiest way to look at them. So they don't necessarily, even if they compute the same thing, even if it's kind of single instruction, multiple data, even then, they do not need to do the same thing at the same time. A thread can lag behind, can run ahead of its peers. So basically, you don't know that. But at certain points, you're going to have a barrier. And that barrier is going to synchronize. That is going to make sure that all the threads that arrive there stay there up to the point when all threads arrive at the barrier, and then they can continue. So that's your typical synchronization in OpenMP. Okay. So what you essentially have is fork join. So if you're familiar with the pthreads interface, you know that you've got a fork, which means create a new thread, and then a join, and that the execution of that thread, that's basically the fork join model. So you see it here. We've got a sequential part, then we have a fork, we get a parallel region with a team of threads, and then you join at the end of the parallel region. That was stupid. Okay. So basically, here they join, and then this can continue and so on. Okay. So essentially, the master thread is always going to be active. Whether the master thread is one of that team or not is implementation dependent. Typically, yes, but need not be. The specification doesn't say so. Okay, so the first construct which you need, because otherwise nothing interesting is going to happen, is create a parallel region. And that's very straightforward in both programming languages. You just say, well, okay, OMP parallel and OMP parallel. Anything in between, the whole block of code in between, is going to be executed in parallel. Similar for C, C++, we have pragma OMP parallel, and then either a single statement or a block. A block is curly brackets and anything in them. Okay, so that's quite easy. We don't have an end pragma in C or C++. All right, so the syntax for OMP parallel, and actually it's also the template of the syntax for any OMP directive. We have a certain directive, in this case parallel, and then a number of clauses. And these clauses determine the properties of that particular, in this case, parallel region. So how do we do this syntactically? Well, basically, there is simply a list of these clauses, and they are typically in C, C++, separated by commas. In Fortran, you can choose. You can separate them by a comma, or you can just have them after one another without any thing. One thing which you must realize is that both in C and C++, the pragma ends at the line end. So if you want multi-line directives, you have to use products. Otherwise, it's not going to work. Okay. So clauses can be many things, for instance, private and shared. And you can already guess what they mean. If and what they contain is a list of variables. So essentially, if I say shared, it means that all the variables which are listed in that directive will be shared variables. If I put a list of variables in private, that means that each thread will have its own private copy of that. But there are more clauses, as we will see later. Okay, so OpenMP directive format, basically pragma, etc., etc. Don't forget, C, C++ is case sensitive. The pragmas are also case sensitive. Just something to remember. Okay, one of the things which is useful to do is to check whether the compiler actually supports OpenMP. And there is a convention for that, and that is that if this particular macro is defined, so underscore OpenMP is defined, then you are dealing with a compiler that supports OpenMP and that is compiling OpenMP. So what you will typically see in C, C++ code is something like this: if def OpenMP and if, and then something that uses the OpenMP library, because that function which is being called there, the OMP get num procs, that is actually in the OpenMP library. So that's a C function that can be called from C or C++. But of course, only when you are in fact dealing with an OpenMP compiler or a compiler that is doing OpenMP. And if you want to use those functions, you have to include omp.h. And it's also good to guard those in the same if-def construct. Okay. So that is quite simple. Then same thing but different for Fortran. So you can also do the if-def thing for block. That's the same. The directive is going to start with exclamation mark $OMP. That's just convention. So exclamation mark says it's a comma. It's a comment. That's all it does. This is for fixed source form. Yeah, I hope to the bottom of my heart that no one is using fixed form Fortran anymore, because yeah, that's the 5+1 column thing and then 72 characters and yeah, well, okay, line numbers and such. So let's not go there. So one of the things is conditional compilation, and this you can actually do with exclamation mark $space. And that means this is only going to be compiled when you're actually doing OpenMP. So that is quite convenient. So an example here is indeed, again, getting this number of processors here, OMP get numprocs. And that, of course, is only available when you've got your OpenMP. And basically, this is guarded by this conditional compilation thing. So if we don't have OpenMP, that entire statement is just going to be ignored by the compiler. All right, how do you get the library? Very easy, use OMP-lib. Quite straightforward. Okay, so of course the important thing here is data scope. And we have a number of clauses in order to deal with that. I actually already listed a few. So we have shared and we have private. So private is and then a comma separated list of variables. So basically that means that these variables will be, each thread will have an instance of that variable of its own, not shared. But be aware that if you have a variable which you assign a value in the master thread, then you declare it private in each thread, for each thread, it will not be initialized. So that's a very interesting trap to fall into, something that you really need to know. The other directive, the other clause is shared, and that's of course just the opposite. So basically it says that any variable which is listed in the shared clause is going to be a shared variable, shared among the team of threads which we're talking about. So that is quite easy. So here's an example. Essentially, well, not an example, but something that you need to know. But okay, we're going to talk about that later, so let's skip it for now. Okay, so that was one thing. I already mentioned it, why can't I remember this word today? It's horrible. Okay, whatever. The thing we just talked about. So now we are going to talk about environment variables, which you can use to control the thing at runtime. So an important one is OMP num threads. That is going to tell the runtime compiler to use at most this number of threads, which you specify as an integer value. So that is quite convenient. You can do export OMP num threads equal to something if you're in Bash. If you're in a C shell or 10x C shell or something like that, you would use setenv in order to define your variable. So yeah, nothing special there. There are a couple of others. So for instance, OMP schedule. We'll discuss that in detail later. So that's also controllable at runtime. So that's nice. We'll see what that is useful for. And then there is a runtime library. We already saw at least one function. So OMP get numprocs. That is going to give you the number of cores in your system. You also have OMP get numthreads. That's the number of currently active threads and OMP get thread num. That is going to give you an identifier which is unique for each thread in the team. It goes from 0 up to the number of threads -1. So this is something that you can compare a little bit to MPI comRank. That would be OMP get thread num, or MPI comSize, which would translate to OMP get num threads. Okay. So here's an example. For instance, OMP get num threads, which I already mentioned. In C or C++, in Fortran, it's the same thing in both languages. Of course, remember C is case sensitive, so it's lowercase. Typically, what I do is the same applies to MPI. When I write MPI subroutines in Fortran, I'm going to use the same convention for the naming as in C. So in C, there is a specific convention with uppercase and lowercase. I'll follow that in Fortran. I'll also do the exact same thing here. So I'm not going to write OMP get num threads in all uppercase. I'm just going to use lowercase because that's the exact same thing as I would do in C and C++. And life is complicated enough as it is when you switch languages all the time. So don't invite trouble. It typically party crashes anyway, so you don't need to invite it. Okay, so here's another example, OMP get thread num. As I mentioned, that gives you the individual thread ID of a certain thread. Okay, other things which you have is a portable timer. So basically you have OMP get W time, so get wall time, and that gives you the time, and it returns that in double precision in both programming languages. So that's convenient if you want to time certain parts of your code, then you can do that. So basically, one thing which you should be aware of, it's a remark which I also made about about MPI libraries. So also in OpenMP, nothing says that the time in one thread is exactly equal to the time in another thread at a given point in time. So they may be off a little bit. So you can only use OMP get W time to measure the time in a thread, not to compare timings, well, to check synchronization between threads, because no one says that at given time, absolute time, atomic time t0, that you would report in the same thread, in different threads, the exact same time. So that is just not guaranteed. You can't rely on that. Okay. You can also get the number of ticks. So that is basically the period of your yeah, it's the period. Yes, it's the period of your CPU. So essentially, it's 1 over the clock frequency of your CPU. All right. So other stuff which is in the OpenMP library, as I mentioned, is locking mechanisms. So to do explicit locking, I would strongly recommend not to do it unless you have a really good reason, because using locking means that you can get deadlocks. A deadlock is a situation where one thread is waiting on another and the other is waiting on the first. And nothing happens anymore, your execution stalls. That's something you want to avoid because that eats a lot of wall time and doesn't produce anything. So that's something that you definitely want to avoid. The nice thing is, as long as you don't use locking in OpenMP, you're never going to have a deadlock, ever. Easy. While, for instance, in MPI, if you make a programming mistake, you can have deadlocks and good luck finding them. So that's an advantage of OpenMP, as long as you don't use locking. All right, so let's do a little exercise. First, I'm going to do a poll. and I'll do it in two parts, one for the online and one for the in-person people. Let's start with the online people. Because what I didn't ask is about your programming language. So I'm going to restrict the number of choices to just C, C, and C, C++, and Fortran, because basically OpenMP is restricted to those. So, okay, how about Room? What are you using? C++, Fortran, Fortran, C++, C++, C++. So majority C++, two Fortran if I counted correctly, and the rest is C++. We are 6 here. Okay, so that's 2 to 1. And online, we've got 4 C++ and 2 people are doing Python or Julia or something like that. Or MATLAB, who knows. Okay, so basically the majority is C++. So that means I'll do the majority of the demo coding in C++ or in C. I'll just go C probably, we'll see. It doesn't really matter too much. And for Fortran, it's typically easier, so you shouldn't worry too much. I'll do some examples as well in Fortran. Because the C++ people can easily follow the Fortran code as well, so that is always convenient. And as opposed to MPI, where I need to spend half an hour on a specific Fortran topic, I fortunately don't have to do this today, because essentially, as usual, the life of Fortran programmers is easier than the life of C programmers. So, well, okay. So the first exercise, let me switch back to, yeah, let me end this poll. Let's start with that. Okay. No, that was not okay. Here. Yep. All right. So the first exercise is essentially very easy. So what do we want? We want to start using runtime library. Yeah, pretty obviously, because that's OpenMP in the first place. We want some conditional compilation. So that's for C, C++, the if-def thing, for Fortran, the exclamation mark $ space thing. Then we want to fiddle a little bit with environment variables, and we want a parallel region with private and shared clauses. And what we want is a sort of hello world. So we have a parallel region, each thread is executing. It's going to report its thread ID. So it's num thread, thread num rather. And one thread, pick your favorite, is going to say, well, okay, there are a total of so many threads, depending on how many there are in the parallel region. Okay, so essentially, this is very much an hello world kind of thing. Okay, why is this my rank rather than my ID? But okay, let's not go there. All right, so yeah, another small poll. How are we going to do this? So essentially, there are a couple of options, or it can be a mixture of both. So I can do the coding and you can watch. You can do the coding and I watch you. You can ask questions. Or we can do it kind of at the same time. So what do you prefer? And now I'm mainly looking at the room because those are in fact people who are most affected by this, since, for instance, yeah, fixing code remotely is possible, but yeah, somewhat more challenging. It's possible. If if you have a problem, I can ask you, I can allow you to share your screen and I can watch it. But anyway, so what do you prefer? Which formula do you prefer? Who likes to do it by him herself? No one. Maybe reluctantly, someone. Not really. Not big enthusiasm. Okay. Who prefers to do it together? So I start typing, you follow along. Okay, those are a few people. Who prefer not to code at all? Who would prefer ChatGPT to do it for them anyway? Maybe all of us, but I don't think we're that far ahead already. That might be very interesting to try. Okay, I've never tried what it can do with OpenMP. Interesting. Anyway, okay, so maybe let's do the thing together. That is probably the most efficient. For later exercises, we can see how it goes, but the first one is probably easiest if we kind of do that together. Okay. What do you need? You need a compiler, and you can choose. You can use either an Intel compiler, which is very good, or you can use GCC, which is for OpenMP okay. So, and this is one of the occasions where I, for performance reasons, really prefer Intel. Because the OMP runtime that comes with GCC is not that good, to be honest. So this is where you actually want to start using Intel compilers. The good news is that the licensing model of Intel has changed. So previously, if you wanted to use an Intel compiler, you could, for free, as long as you used it for work, you were not paid for. A very interesting license. I've been talking like half an hour with people employed by Intel about their licenses, which they did not understand. But okay. Anyway, so that was the case in the past. So I couldn't even use an Intel compiler for teaching without paying for it. Now we have licenses on the cluster, so that was not an issue. But nowadays things have changed. You might be aware that Intel now is switching to an entirely different implementation of their compilers, which is a very interesting exercise. And that is their entire ecosystem of one API. And in fact, the license is extremely liberal. So basically, with one API, essentially you can do whatever you want, more or less. I don't know how it works if you are really developing commercial code. This I don't know. I never checked. But for anything that is academic, open source, and so on, just use it, even if you're paid to do the work. No problem. How can you work with one API if you feel so inclined? There are many ways you can install it. There are distributions for it which you can install with your package manager of your Linux system. What I typically do in such a case is I create a Singularity compiler out of their Docker images. And then I get a very nice developer's experience that works quite nicely. I'm not going to use that today. Yeah, I have an image on my laptop, which I could use. Okay, maybe I can show you later. But I'm just going to use GCC G-Fortran for now. It does the job, but yeah, there is a performance thing. Okay, so let's start coding. Yeah. That is very unlikely. I don't know what is installed on these PCs. If you have a virtual machine thing, then the answer might be yes. It doesn't open. Okay. then the answer is likely to be no, to be honest. Is there WSL installed? The answer is very likely to be absolutely not at all. No way in any. Yeah, well, it doesn't immediately say no, so that is already something. But it also, in the end, is not doing anything, so I'm afraid the answer is no. If you have a VST account, if you have your key with you, then the answer is yes again, but okay. Yeah, what I'm using on my laptop, this is a Windows laptop. So I'm using WSL, Windows Subsystem for Linux, in order to do some decent work on Windows laptop. And I've installed a GCC compiler. Don't remember which one. I think it's GC 11.3 at the moment. So not the latest, but a fairly decent one.
Excuse me, I have a question. Can you hear me? Hello?
So one of the things in the exercise was that we should use conditional compilation. So our application should also produce correct results, even if it's not compiled with OpenMP and if it's running with a single thread. So that was the condition. So that means that I have to guard the include of OpenMP.h with the variable which ought to be defined if I'm running with an OpenMP compiler. Okay, I've got my main, which returns 0 at the end. Nobody cares. And then I need two variables. I need a variable to store the number of the thread, so the thread num, and another to store the number of threads. Okay. So those will be integers. And let's initialize that to -1. It's never going to be that, but that's just for initialization. And int num threads, preferably stored correctly. Let's put that to 0. That also should not happen, but this really makes sure that we are on the same page. Okay, so what I want is, but maybe let's not do it this way, because if I do it this way, that's nice in order to show you something, but let's do it correctly first and then fiddle a little bit. So suppose that I'm running this as a sequential application, so just something that runs serially, no OpenMP. Then reasonable values would be 0 for the thread ID and 1 for the number of threads. So let's just initialize them to those to start with. I wanted to show you something, but let's not do it now. Oh yeah, I can still do it anyway. Doesn't matter. Okay, so this guy is going to be 0, and that guy is going to be 1. Okay. So now, what I want to know is the number of threads. So that's simple. I can simply call OMP num threads and OMP thread num. Easy. But if I'm doing that in this part of the code, then the answer is going to be 0 and 1. Because the current team of threads consists of the master thread. Okay, even if I run this, I compile it with support for OpenMP, I run this with OMP num threads is 512, which would be a stupid idea, but even then, if I were to call at this point in the code OMP num threads, the answer would be 1. So if you want to know the number of threads which you have, and you want to know how many you have in a parallel region, okay, first open a parallel region. Okay, so let's do that. Pragma OMP parallel, easy. Okay, so that means that all the code which is here, and I'm just going to create a block here. So the OMP parallel directive is now applicable to everything in the block. So everything there is going to be done by every thread. Okay, so now I can determine the number of threads in the team right now. So in this parallel region. So basically, num threads is going to be OMP get num threads and thread num is going to be OMP get thread num. Very easy. Yeah, of course, except that this is not going to compile unless I've got an OpenMP compiler. Because if I don't have an OpenMP compiler, OMP num, get num threads and get thread num are not going to be declared. So this is not going to, well, it's going to compile, it's not going to build. The linker will say, I don't know, go away. So I have to do this conditionally. Now I can do two things. I can do that within the pragma, or I can even do that outside of the pragma, whichever, doesn't matter that much in this particular case. But basically, since I'm guarding the call of the library functions and other things might be happening in this particular thread, maybe it's a good idea to do it here. So if def OpenMP, okay, and if. All right. And then the last thing to do is to just print stuff. So print thread num, and if thread num is equal to 0, print f num threads. Okay, and this of course I can happily do unconditionally since my variables haven't been defined, initialized with the proper use. All right, so maybe I didn't do too many stupid things, so let's try. I'm going to compile this, so I'm using GCC because this is C code, -f OpenMP. That's the same option for G++, that's the same option for Fortran. It's all the same thing. And then, of course, the name of my executable, of my thing here. Okay. So I'll get a.out. And when I run it, you see that it's being executed with a total of 16 threads normally. It should be printed somewhere. Something is not printed. Why? This is weird. Thread 0 doesn't seem to print. What did I do? Thread number. Yes, this is interesting. Why is thread number, the number of threads not being printed? This is very clearly a bug. Let's try and run it again. Maybe this time it works better. Not really. Let's try it with a few lesser threads. Let's try it with 2 threads. Still, it doesn't. That's annoying. What's going on? Let's get back to the code. What's going on is that I actually have a race condition. Because I didn't specify the fact whether thread num was private or shared. There is no clause, no data clause on my parallel. That means that the default applies, and the default, if I don't say anything, then it's shared. Okay, does that explain? Well, yes, it does, because what is going to happen? Thread 0 is executing, okay, but its value of the value of thread num may be changed by it and set to 0. But then, of course, thread 1 or thread 5 is also executing and setting that shared variable to its appropriate value. So thread 0 keeps on using that shared variable, which meanwhile may or may not have been changed, but in this case has been changed. And so it's never going to be equal to 0. So what I have to do is to make sure that I don't have a race condition and that the variable which I intend to be private, thread num, is private. So I have to add a clause to parallel. Let's see whether that makes a difference. And now indeed, we get 16 threads total. You see it on line 3 of the output. So now it's actually functioning correctly. So basically our num threads is still a shared variable, but our thread num is now a private variable. And now, of course, there is no race condition anymore because each thread will have its own copy of that particular variable. It will initialize it and it will do the right thing. Okay, let's see whether the other condition is also fulfilled, because we wanted this program also to function correctly when we don't have an OpenMP compiler. Okay, that's very easy to simulate, just leave out the -fm OpenMP flag. So let's compile that again, but now without -OpenMP. Okay, a.out is 1 thread in total, thread number 0, that's it. So it compiles, so that's good, and it also executes correctly. Okay, so that's basically our hello world in for OpenMP. And it already showed us that, yeah, you can have a problem if you're not careful with the scope of your variables. If they're shared, you may get race conditions. All right. Any questions about this? Everything clear? Also for the people online? Okay. I'd say time for a break, and then we can continue. So we can do two things. There is a list here for the participants to sign. I'll also check people online and check them off. But please sign, that's for your certificate. And there are tokens here. They're just enough for each of you. I'll get more for like. Okay, so let's say 10 minutes break, something like that. So that means, okay, let's make it 10:55 to resume. I'll stop sharing. Well, put announcements. Okay. Yes, I can quit. Go back. All right. There seems to be a question online. Feel free to either. That's in the chat. Okay, I'm sorry. I didn't notice the chat. Yeah, indeed. The if condition outside. So with the if condition, you actually mean the conditional compilation. Yes, you can also do that. That is also something you can do. It depends a little bit on what you want to do. The point is, of course, that the print statement should go into the parallel region. So if you put the if statement outside of that, you would have to have an else in your preprocessor if def else and if and that would be duplication of code. So, but it would be possible. I'd not really say it's easier, but it's possible. Okay, so break until 11. Sorry, 10:55. All right. So feel free to help yourself to yeah, for those of you who are not familiar with proceedings, so there are vending machines that you leave the room and you turn right and left. Or there are two vending machines, one for coffee for token. Well, there are two vending machines. One for soft drinks, which you just pay in euros, and also some snacks and stuff. Again, paid in euros.
Where are we? You are here running. Do you have GCC in your PC? Do you have the compiler in your PC? Yep. The C compiler there. Since I was one here. Actually, the confirmation says it requires 1.5 euro. When you put this, it's value of 1 euro. So short of 50 cents. Of course, I was the lucky one where it was 1 euro.
Yes.
Okay. Can we continue? Probably yes. Did everyone sign the participants list already? Nobody did not sign it. Okay. Right. Then let me put that away. Everything that's safely stored away can't be forgotten or left behind somewhere. So, okay. That's it. Now, let me share my screen again. Yeah. Okay. So there is a question in the chat whether I can show the code again and also the way to compile. Yes, I'll do that. Let me first share my screen and then I can indeed do so. So I want to share my entire screen. Go. All right. Okay. I'll try to keep a better eye on the chat. Normally I should get a beep. I don't get a beep for some reason. which is a bit weird, but okay. Yeah, I wanted to show you the code. Yeah. So the compilation thing is gcc-openmp and then the name of your file. So hello world.c. So now we have an OpenMP version. The code is this. So basically, it is opening a parallel region, declaring that thread num is private, and then modifying the values of the num threads and thread num variables in each thread. Well, actually, each thread is in fact getting the total number of threads, which is a bit a waste of time because in fact only thread 1 is using it, thread 0 is using it, but then again, that doesn't matter too much. Okay, is this all right for the Fortran people as well? Did it work out for you? Well, shouldn't be too difficult. Okay, let's continue in that case. All right, so okay. All right. So up to now, we've officially only seen one OpenMP directive, and that's the parallel directive. So basically, that means you open a parallel region. Everything which is in that parallel region is done by all threads in that region, in that team. So that's not particularly exciting. So how can we ensure that works get divided among the members of the team? There are a few mechanisms for that, and that's what we are going to talk about right now. So essentially, the question is which thread is going to execute what part of the work. And we can do that using work sharing directives. Then, of course, we have to talk about synchronization and about the master thread as well. Okay, so essentially, we are going to get some organization, some management in the parallel thread world. Okay, so work sharing constructs, we have a number of them, and basically they are intended to divide the work among members of the team. That's essentially the idea. They, of course, only make sense within the context of a parallel region. You can't have a work sharing directive outside of a parallel region because there is no one to share it with. Doesn't make sense. So that is important to remember. And what is also important to remember is that they don't launch additional threads. So the fork join model, you first have parallel that will fork. Work sharing directives just divide the work. They don't create more threads. That's something they don't do. That's what parallel is for. So then what is also important to realize is that there is no barrier upon entry in a work sharing directive. First thread that comes there starts doing its part of the work. That's important to realize. No synchronization at the beginning of a work sharing directive. We have a few. So there is the sections directive, which personally I find somewhat useless. But yeah, it's there. Sometimes it can be useful, but not very often. Then depending on your programming language, there's either for or there is do. Do for Fortran, for C, C++. And of course, you can already guess that that is going to divide the work, which is done in a loop. And that's the idea. Then there is also specifically for Fortran the work share directory. We'll see how that works. And also the single directive. Okay. And then, of course, there is task parallelism, but this we'll deal with later separately. So this is an example of the sections directive. So you start a parallel region, then you have a work sharing directive sections, and each of those sections can be handled by a different thread. So that means that in this particular case, at most, 4 threads can be active in this sections region, in the section put to work by the work sharing directive. So this is something that is determined at compile time, and that makes it less flexible. And there are not that many real-world examples where I would say, okay, this is really useful. If you look at old OpenMP tutorials, then you would sometimes see sections being used recursively. So they would exist in a function, and then a function would open it would create two new sections. Each of those sections would create 2 new sections, and so on. So that's a cute idea, but at the time it was completely wrong, because that was not supported by OpenMP, and it could work by accident. So no, don't do that. Bad idea. If you want to do something like this, use tasks. That's what they have been invented for. It will work, but it's really not the best approach. Okay, so that's the way it works. You mark each section with a section directive, and the first one is implicit. So here we have 4 sections in total. Okay, here's the same example, but now in Fortran. So OMP section is an exception. I mentioned, okay, in Fortran you always have a directive and an end directive, not for section itself. For sections, plural, of course, you have begin sections, end sections, sorry, but you don't need to put an end section for each section which you define. Just an exception to the general rule. Okay. So basically, the syntax is pretty straightforward. You have just the sections with 1 or more clauses, or 0 or more clauses, and each time you have a section with a new line. You can, if you want, have 1 section directive per section. So the first one is optional. You can put it there, or you can just say, well, okay, the first section is implicitly defined by the sections directive. Doesn't matter. And the same in Fortran. So no big surprises here. And as I mentioned, not particularly interesting. The core of OpenMP up to OpenMP, let's say 3 something, was in fact this directive, the for directive or the do directive. So here's an example for C, C++, Pragma OMP4. Note, it occurs obviously in a parallel region. Otherwise, it's not going to be interesting. And what it is going to do is it will divide the iterations of the loop over various threads. So for instance, in this case, there are 4 threads. There are 20 iterations. So each thread is going to do approximately 5 iterations. And by default, you have no idea what happens. But what typically will happen, it's not in the specification, but what typically will happen is that the first thread will do the 5 first iterations, the second thread the 5 consecutive ones, etc., etc. That's what usually happens. It's not specified, so that's if you rely on it, it's undefined behavior. Shouldn't do that. We will see how to control that and to make sure that if that is what you want, that is also definitely going to happen later on. Okay, so same thing for Fortran. OMP do, OMP and do. Very simple. Okay, so again, the syntax. very simple OMP for, OMP do with some clauses. Okay. One thing which is important, a distinction between Fortran and C, C++, the do loop in Fortran is pretty straightforward. You have an iteration variable, you specify the first value, the last value, optionally a step. That's it. That's your do loop in Fortran. There it ends. End of story. In C and C++, of course, with for loops, you can do many things. They need not have an initialization. They need not have a condition. They need not have an increment. They can have and conditions, I mean logical expressions as conditions, which have even nothing to do with your iteration variable, etc., etc. All of that is not allowed. You need to have a for loop in C, C++ with a canonical form. So basically, what is a for loop with a canonical form? Well, it's here. We have an integer type. That's already important. So you cannot have a for loop that goes over double precision. It can go over int, over long, over character if you need to, but not over float or double. That's not allowed. That's not canonical form. Okay, so you need to have your initialization of the variable, loop variable to the lower bound. You need a condition, and that condition is also pretty restricted. It is just a comparison to the upper bound, which must be known at runtime. It can't change during the execution of the loop. That's not allowed. And then also the increment part is also restricted. We can increment the loop variable, we can decrement it, of course, and we can add a fixed increment each time. That's it. No fancy things. That's your canonical form. It will actually warn if that is not allowed. Of course, in C, you can also use pointer types because those are in fact integers. That's possible as a loop iteration variable. And in C++, you can use an iterator, but then it should be one on a data type that allows for random access. For instance, std vector will work. Vol array will work. List? Nah, not really. So basically, that is something to keep in mind. Also, the lower bound of your loop, the increment and the upper bound, the B, should be invariants of the loop, so you're not allowed to fiddle with them. They must be determined when you enter the loop, not changed while the loop is executing. So that's canonical form. That's all kinds of things you can not do in C or C++ if you want to. Probably not, having canonical loops is not a very good idea anyway, but okay, that's a different discussion. Okay, so a bit more details. What can you have as clauses? Because that's where things get interesting. Of course, what you can have is private or shared. So that's something that you can definitely do. Then reductions is also interesting. We'll see why they're useful later on. You can also have collapse. What does that mean? Well, basically, what you often have in scientific code is nested loops. Do loop, do loop, do loop, whatever. For loop, for loop, for loop. So if they are independent, and if the boundaries are independent, you can actually collapse them together. So all the iterations of all those loops, so essentially all the iterations of the inner loop, will be the whole parallel space. So that means that if you have, let's say, a for loop over I, and I can have n values, and you have a for loop over n, and n can have m values, and you use a collapse of 2, then you will have a space of m times n things which can be done in parallel. If you don't use collapse, you would just have n things which can be done in parallel, the iterations over the outer loop, in this case I. So collapse can or cannot be useful, it depends. A context where it is very heavily used is in GPU offloading. There a collapse is very important. On CPUs, I don't see that much of a benefit typically, but it's something worth trying. Okay. Then also the schedule. We'll talk about that in a minute. And a no wait. Things get interesting. What we mentioned was for workshare directives, we don't have any synchronization at the beginning of the workshare directives, but we do have it at the end of it. There we have synchronization. So basically that means if I have my parallel for loop, the first thread that arrives, that does all its iterations, is just going to sit there at the end of the workshare directive and waiting for all the others to come. It's only when all have arrived that the thread may proceed. So there is an implicit barrier at the end of a work sharing directive, at least for do, for sections, and so on. You may or may not want that. If you don't want it, you say, well, okay, it's fine. This thread can continue with whatever it should do after this particular for loop. You can specify a no wait clause. And then if a thread arrives at the end of the work share directives, it's just going to continue with the code below that, which comes after it. So that's important for performance reasons, because that allows you to avoid synchronization when you are sure it's not required. That last part of the sentence was crucial. Because of course, if you make a mistake there, you'll get race conditions. So if you are sure that you can use a no wait, make sure that you're really, really sure. Okay, there is a difference between C, C++, and Fortran with the no wait. And it makes sense. So obviously for C and C++, the no wait goes into your directive. It's a clause of your directive. Easy. For Fortran, they have decided to make that a clause of the end do, which makes sense because that's where the no wait is relevant. It's at the end of your work sharing directive. So in a way, it makes a lot of sense to indeed syntactically impose that it comes where it ought to go in Fortran, which is at the end of your work sharing thing. So that's a slight difference between C and Fortran. But again, it makes, in my opinion, a lot of sense. Anyway, the schedule clause. So the schedule clause determines for a loop which iterations are done by which thread. And you have quite a lot of choice here. The most trivial one is static scheduling. And static scheduling is pretty straightforward. You just say, well, okay, I have 20 loops, I have 4 threads. First 5 iterations are for thread 0, second 5 iterations are for thread 1, etc., etc. Easy. Okay. Or you can optionally set a chunk and then you divide up the number of iterations in that way. For instance, I've got my 20 iterations and I set a chunk size of 2. Then the first two iterations will be done by thread 0, the second 2 by thread 1, etc. And then the iteration 9 and 10 will be done by thread 0 again, etc., etc. So it's a round robin thing. So this is static scheduling, and usually that's the default. But it's not specified in the specification, so you cannot rely on it. If you want static scheduling, just put it there. Okay, then dynamic. So basically, again, we have the chunk size is by default 1, typically not what you want, but okay. So this is useful when you have load imbalance. What do I mean by load imbalance? one iteration may take longer than another iteration. If you have that, static scheduling can be a problem, because it might be that one thread has a lot of work and another thread has very little work. And yeah, that means due to synchronization, all the threads except the one with the most work are going to spend waiting time at the barrier. So that's important to realize, and that's where dynamic scheduling comes in. In dynamic scheduling, a thread gets a chunk, so a few iterations to do. As soon as it's done, it gets the next chunk. As soon as another thread is done, it gets its next chunk, etc., etc. So in that respect, this is an interesting schedule to deal with situations where you have load imbalance. For instance, suppose you have a loop over a matrix, but you iterate over all the rows, but only the columns in the nested iteration, only over the columns starting from the diagonal. So basically that means that for the first row, you do as iterations the whole row. For the second one, it's one element less. For the third one, it's two elements less, etc., etc. The last iteration will do only trivial computation on the one element which is on the diagonal. So that would be a typical situation where with a static schedule, you have a deep problem. Because the first thread is going to have to do a lot of work. The last thread is hardly going to have any work. And yeah, bad situation. Because, well, the last thread is going to sit there and wait. The one but last thread is going to arrive a little bit later, but also sit there and wait, and so on and so on. So you will have a very unevenly divided work. So that's where dynamic scheduling comes in. Even more interesting is guided, and that basically means that you get exponentially decreasing chunks. So each thread gets a large chunk to begin with, but its second chunk will be a bit smaller. And progressively, the chunk size will decrease. So why is that nice? Basically, again, for dealing with load balance, it can be very useful because you start with a large granularity for each thread. Each thread has quite some work. And then gradually, work remains. But if you assign increasingly smaller chunks of work, it all fits better together. So fitting in work gets easier with smaller chunks. And you have the best of both worlds. You start with large chunks, so compute, very little overhead. And then progressively chunks get smaller, and they fit in better into the whole scheduling thing, and you may end up with a very nice division of work. That's basically the idea. Okay, and then there is auto. Yeah, figure it out, do something, do your thing, whatever, leave it to the runtime. Okay, yeah, you can do that. Feel free to try. And then there's also runtime, and that's nice because that allows you to control the schedule using an environment variable. So this is nice for benchmarking because I can just say, well, okay, I've got my parallel for loop. Okay, I'm going to time it. And I'm going to compile and link my code. I've got my executable. And then at runtime, I'm going to decide on the schedule. And I can run it with static, with various chunk sizes. I can run it with dynamic with various chunk sizes. I can try guided. I can try auto. I don't have to rebuild my application. I just have to set the environment variable to an appropriate value, and I can benchmark. Of course, if you select runtime and you have multiple schedule clauses on multiple for things, yeah, then basically it's one for all. So all of a sudden, all your loops will be static, or all your loops will be dynamic, and so on. So do this one by one. Otherwise, you get something very weird. and you have no clue what you're looking at. But it can be very useful to save some time in benchmarking. But again, do it loop by loop, because otherwise it gets interesting. Okay, so as I mentioned, default schedule, nobody knows. As far as I know, it's usually static with chunk size 1. Well, not with chunk size 1, basically with evenly divided among the threads, simply. But you can't rely on that. Okay, so this would be static. So basically the colors denote the thread ID, essentially. So in this particular case, you may end up with one thread which has a little bit less to do. And which thread gets less to do is basically up to the implementation. So in this case, we in total have 13 things to do. So you can either do that as 553, or you can do that as 588, as 544, but that is implementation dependent. You don't know what's happening. You don't have control over that. Does it make a difference? Well, sometimes a little bit. Okay. One thing which is very important, if you have static, and in the same parallel region, you have consecutive for directives, then for static, the division of work for the loops, if they have the same number of iterations, will be the same. That is guaranteed. So that is something that the specification requires. And I will make a remark on that later on, because that may have an important performance impact. This is really important that that happens. Okay, so this would be dynamic, depending on who ends first, gets the next one, etc., etc. And guided, you get chunks of decreasing size. So thread 0 starts with 3 items to do, and then it gets, okay, the colors are not so easy. I think that is, which is in the center now, is thread 0 again, and so on. So they get decreasing chunks. Okay, and auto, yeah, whatever. So this is under your control, and this impacts performance. Depending on the type of the work you're doing in each iteration, you may choose one schedule over another, depending. Okay. In Fortran, you have the work share directive, and essentially that means it's a little bit similar to the do concurrent, which is actually standard Fortran. So basically what you're saying is, okay, I've got a matrix computation, and it's an element-wise computation. Do your thing. Compiler, figure it out. Okay. So how this is done is completely up to the runtime, up to the compiler. Okay. Try it if you like, see whether it helps you or not. It may be that explicit loops are better. It depends on the situation. Also on the quality of the runtime engine. So, okay. Then the single directive. So basically, only one thread of the team is going to do that. Which one? You don't know. Maybe master, maybe another thread. So this, for instance, you could use for providing feedback while a loop is running. For instance, that you ask one thread to print the number of iterations which you've already done, something like that. So the syntax is pretty straightforward. You just have OMP single. You can have a number of clauses. Nothing special here. So basically, there is an implicit barrier at the end of that. So basically, that means that all the threads arrive at a single directive. The first one is going to do it. All the others are just going to pass to the end and wait at the barrier. So this is synchronizing. If you don't want it, put a no wait clause on it. Because if that single thread is doing a lot of work, this is going to cause a lot of overhead, because all other threads are just going to sit there until that single thread is done with whatever you're asking it to do. So be careful with this. This is dangerous. But we need it later on for tasks. You will see why it is actually a very useful thing. Okay. So that means that, for instance, in one parallel region, you can have a part of your execution which is in fact not parallel, which is just serial. And that's done with a single directive. Sometimes it's useful. Mostly you have to be careful. Okay, time for a second exercise. So basically the idea is to compute pi. And in this particular case, we are going to use this formula here. So essentially, we're going to do a quadrature of the function 1 divided by 1 plus x squared. And we do that from 0 to 1, and we multiply by 4, and that gives us pi. Great. So basically, what are we going to do? Well, we are going to use some quadrature method. A very simple one, of course, is to just say, well, okay, I'm going to choose points in the interval 0 to 1. They will be equidistant. All the values will have the same weight, which is just 1. You just sum the lot and you divide by the width of the interval, which happens to be 1, and delta x, whatever delta x is, and that will give you the value of pi. This is, of course, just a plain for loop, so that's easy, and that will be very easy to parallelize. Okay, let's try. Let's start with the serial version. So we work in double precision. Okay, I think I'm going to switch to C++ here. All right, so Okay, so I hope I didn't do too many stupid things mathematically. Let's just see. Yeah, okay. Okay, we get indeed something that kind of resembles pi, so the implementation seems to be reasonable. Okay, that's good, that's our baseline. And now we can parallelize it. So that will be kind of interesting because question is, how do we do this? Well, the obvious thing to do is to say, okay, pragma OMP parallel for, that's good, that's going to divide the work. Okay, one thing I know from the standard is that in fact the iteration variable of the do loop I'm now parallelizing is going to be private automatically. I don't have to worry about that. I can make that very explicit if I want to, but I don't really need to. In C or in C++, the scope of variables can be local to a block. So in this particular case, X is local anyway. So given that it is local to an iteration, it is by default flat local. I don't have to care. In Fortran, I have to be a bit more careful because of course I have only variables that are, well, global in a subroutine, well, in a procedure or in my main program. So in Fortran, I would have to be careful with X. I would have to declare X private. That's where you hope that blocks would do something useful. Don't even think it. So essentially, I would have to say that X is private. Here in C or C++, I don't need to because I declare it as a local variable in my loop, so it's private automatically. Okay. What else have we got? We have pi. Yeah, but this is going to be interesting. Let's just ignore it for now. But pi is going to be a shared variable because obviously each thread needs to update it. Agreed? So it needs to be shared. Okay. One of the things you can do, it's not mentioned yet, you can change the default for the scope of variables. So by default, the variables are shared. But if I don't want that, if by default I want to make them private, I can say default private. Or I can explicitly say default shared. But I can also say default none. And that's something I personally like a lot, because that means that if I don't explicitly say that a variable is private or public, the compiler will say no go, error. I won't compile this until you explicitly declare every variable that is used in this particular construct, whether it is private or shared. So typically I switch that on. And I do that by saying private is none. Okay, but then of course I have to be explicit and I have to say that pi is shared. I don't have to say that I is private because that's automatic. At least I hope so. Let's see. Okay, so essentially I'm done now. I hope. So g++ dash f OpenMP pi. Okay. Okay, yeah, right. It doesn't consider this canonical form. That is ridiculous. Okay, whatever. It's universal initializer. Come on. Okay. And not specified. Aha. Okay. See why it's useful? So I looked at my for loop and I forgot to say anything about n. So it's now telling me that actually I need to say something about n in the enclosing parallel. So that's good. So n is the number of points or the number of iterations if you want. So basically, yeah, that is a shared variable, no problem. Okay, so I can add that. And okay, this is weird. It's complaining about dx. Okay, this I would consider a bug actually, but okay. Let's not quibble. If it's happy, if I say that dx is private, I'm happy to do so. But this I actually consider a bug in the compiler. Okay, anyway, now it should be happy. And it is. Okay, so let's try this. Okay, let's have some iterations. Let's be a bit more ambitious. Let's say 10,000. And we get our value of pi. Well, it's a value. Maybe it's got something to do with pi, but maybe not. What's going on? The problem is with pi. It's shared. So again, I've got a race condition. Why have I got a race condition? I'm sorry for the people online, but the easiest way to show you this is by making a drawing. And I don't have my tablet with me. Making a drawing with my mouse is going to be a little too challenging for my drawing skills. So I'll try to be as verbal as possible about my drawing, but yeah, I can't really help this. Okay, so what have we got? Let's consider just two threads to make things clear. We have thread 0 and we have thread 1. And the thread is going to do something like pi plus equals something something, pi plus equals something something. Each thread is going to do that in each iteration. Seems fairly innocent. We just increment the value. What's the problem? Well, the problem is that pi is a shared variable. That means it lives somewhere in memory. And it has a certain value at some point in time. And let's say we start out with 0. Did I do that actually? I don't remember. I have to check whether I did my initialization of pi correctly, but I think I did. Anyway, yeah, so what's your problem now? Well, the problem is that pi plus equals something something is not an atomic operation. It's actually two operations. In that statement is going to compile to a number of instructions. The first instruction is going to say, okay, load from memory the value of pi at this point in time. Okay, let's say it's 0 at this point in time. Okay, the next instruction is going to say, okay, add something to it. The third instruction is going to say, store that result into memory. So what's happening here? You have the RAM, that's where pi is. If you do a load, you get it to the core into something that's called a register. So that's a very local memory location that is in the core itself. You have a very limited number of registers. It's another discussion, but basically that's where the value is. That's where the increment will happen. And then that register's value should be written back to the main memory. Okay, so that's 3 instructions, not 1. Okay, now things start to depend on the order. Suppose that thread 0 does a load, no problem. It does an increment, no problem. It does a store, no problem. Then thread 1 does a load, an increment, a store, no problem at all. The symmetric situation, thread 1 does a load first, an increment, a store. Then thread 0 does a load, an increment, a store, no problem. Things get interesting when thread 0 does a load, thread 1 does a load. Both get value 0. Thread 0 increments, thread 1 increments, nobody cares. And then one of them, I don't know which, is going to do a store, and then the other is going to do a store. So basically that means that only one increment is going to be in memory. The other one is just going to be overwritten. That's your typical race condition. And you see indeed that the value of pi which we get is less than the one we expect. Indeed, because most of the work which has been done in order to compute pi is in fact just overwritten. Can we, I won't say prove it, but can we illustrate that? Well, let's run this again and let's see what we get, because I don't know how stable this value is, but it's likely to always going to come out similarly. Ah, that's interesting. So yeah, it depends a little bit. But now let me decrease the number of threads. So we are executing with 16 threads. Okay, I'm going to restrict to 2 threads. And now you see I get a different value. I get something that is better. So basically now the race condition is, if for some definition, less severe. Now you see with 4 threads, it gets more severe again, because more of the values are just ignored, because they are overwritten. The corresponding increment is overwritten. The corresponding value as a result of a store is overwritten by another store. Okay, so we have a race condition. The problem is indeed that pi is shared. Okay, what we can't really do is make pi private, because if we do that, each computes its own part of pi, but how are they going to be collected together? They need to be aggregated somehow. So what you would typically do in this case is use a reduction clause. We can do a reduction on pi with as operator the addition operator, so the plus. So that's the easiest way to solve this. We could also kind of do this manually. We could say, okay, I'm going to have a single directive in my parallel. In that single directive, I'm going to malloc an array with as many elements as there are threads in my team. And then based on the thread ID, each thread is going to write its own value into that array. No race condition, because array index is based on thread ID, no problem. And then at the end, after the parallel region, I'm just going to sum up all the elements of the array and I'm done. So that would be a way of doing that. And that is in a way also how the compiler is going to deal with this. But since this is something that occurs quite a lot, actually we can use a reduction clause on pi with plus as an operator. Okay, so let's compile that. All right, and I still have to have it shared, apparently. Pi n, okay. All right. And it's unhappy with something. Okay. I probably need to specify it in a different order, like this. Okay, still not happy. Ah, okay. I was right removing it here, but since my reduction clause was not okay, the compiler got confused. Okay, now we're there. So basically, this is the correct thing. We only declare n shared. We declare that we want to do a plus reduction on the variable pi, and that is then automatically considered shared, which of course makes a lot of sense. Okay, so we compile that. Well, we already did that. So basically, let's run this. And now we get 4. That's interesting. Why do we get 4? Okay, I'm doing something silly here, but the question is what? I times dx. I have my initialization of pi, so that should be okay. Oh, yeah, this is of course extremely stupid. Dx should of course be a shared variable, not a private one. And I misread the feedback of the compiler. I thought it was complaining about x, but it was actually complaining about dx. So this should make a lot more sense. And it's not going to complain about x, which makes very much sense because that would have been completely silly. Okay, yeah, that makes sense. And now we need to specify the number of iterations, and we get something that is very close to pi. Okay, that looks a lot better. Okay, so I misread. I thought it was complaining about x, which, as I mentioned, it really shouldn't, because that would have been stupid because it's local variable. I was really very annoyed with the GCC compiler there, but indeed, in that respect, it did the right thing. And then I somehow still typed dx, but dx is of course a shared variable. And this is a nice illustration of why this was rather silly. because if I declare dx private, it's not going to be initialized in the threads, and it will have some value. Likely in the master thread, it's going to be the original value. In all other threads, it's going to be something, typically some small number. And basically, you end up with a lot of zeros for all the other threads, except for the master thread. And hence you get 4 rather than what you would expect. Because essentially I was just multiplying dx, well, adding dx a number of times and then dividing by, dividing adding 1 over dx and then multiplying by dx and 4, and that gives 1, so that's pretty obvious. Okay, but basically this solves that particular issue. So what happens under the hood? Essentially, what is going to happen is that the compiler is going to generate storage space somewhere in such a way that the value for the addition to pi, so the total increment, can be stored somewhere. Where you don't know, where you don't have to worry about. It's going to take care of that somehow. Each thread will have its own private copy of pi, and aggregation will happen at the end of the work sharing directive. Generated by the compiler, not by you, no problem. So that is what happens under the hood. And that is, of course, quite convenient. So, as I mentioned, if you have a private variable, the master thread may have the original value, but never ever depend on that, because that is implementation dependent. You don't know. The specification says if you have a private variable, it is not initialized. Even if that exists, and it does by definition, even if that exists in the scope outside of the parallel region. Okay. All right. So that computes pi rather conveniently. And of course, what you can do now is do a little experiment with timing and see how much time it takes to compute pi using 1 thread, 2 threads, 4 threads, etc., etc. That's very easy to do. But let's not go there for now. Scaling behavior should be reasonable. Well, maybe it's a good idea to do it anyway. So for n threads, in 1, 2, 4, 8, 16, do echo $n threads. I just want to make sure that I've got the syntax correct. Yes, I have, because basically I hate bash and I always forget the correct syntax. OMP num threads. Okay. Equals n threads. All right. And then what we do is time goes here, I think. And we need a substantial number of iterations. So, and this is 100 million. Okay. So we get a decent value of pi each time, so that's good. We start with one thread, we start with 0.3 seconds. With 2 threads, we have 0.16 seconds. So that's divided by 2, so that's perfect scaling. With 4 threads, I don't think so. We get 1/10 of a second. While we would expect, let's say 32 divided by 4, so 0.8. So already our parallel efficiency is not 1. So for 4 threads, we already have a parallel efficiency, which is like 75%. So not that good. Problem is that there is too little work in this particular case. So this computation goes pretty fast. So that means that overhead due to starting parallel threads, synchronizing at the end of, etc., just outweighs the efficiency. Okay, and as you can see, when we finally go to 8 threads, we get 0.6. So that is rather crappy. We expect 0.4, we get 0.6, so not so very good. And normally I would expect approximately the same time for 16 threads. And it's even worse, we even have a somewhat larger time for 16 threads. Remember, I mentioned that I have 8 physical cores in my machine. This is Intel. So yeah, it supports hyperthreading, but it doesn't share floating point. I'm doing a lot of floating point. So essentially the 2 threads which are on the same core are in fact executing serially, plus there's overhead, because the core has to switch context, which means that it loses time. And hence, indeed, that I don't need to go, certainly I don't need to go beyond 16 threads, beyond 8 threads, beyond the number of physical cores in my machine. Just run it again to see whether that is consistent. So yeah, sort of. Times are a little bit lower. Yeah, it's a very bad idea to do benchmarking on a laptop because basically depending on what it's doing, the clock frequency is going to go anywhere between 2 gigahertz and in this case 4.1 or something like that. So basically numbers will be all over the place from one run to another. But basically you see that results are consistent. Okay, in relative terms at least. All right, so that was this particular exercise. Yes. Okay, so this was sort of the situation with respect to work sharing directives before what I would call 3.1. No, it's not really true. Okay, I know tasks were introduced in OpenMP 3, but okay, not used that much. They get a lot more useful now. So a typical example might be traversing a tree. So if you have a binary tree, that means that each node in the tree has 2 leaves. Well, has 2 subnodes, not necessarily 2 children. And suppose I've got some work to do in each node. And of course, I also need to do work in the children. So that does not really fit well into a for loop. Okay, you could argue that if the work which needs to be done in each node is independent of the other nodes, okay, then you could in C++ implement an iterator, which is, for instance, a depth first iterator or your favorite, doesn't matter. And essentially that would work. I could do that. But of course, if the result of the computation in a node depends on the results of the computation in a subnode, then things get more interesting. Because then how am I going to parallelize that with a for loop? I cannot do that. So that means that if you want to do this in parallel, you need something else. And that something else are tasks. So here is an example indeed of a traversal of a tree. So a node is simply represented as a struct. That struct has some data. In this case, it's just a structure of the tree, but of course there is some data and you want to compute on that node. It's not shown, but that's implied. And you get the structure of your nodes by using pointers. So a pointer to a child on the left, a pointer to a child on the right. If the pointer is null, that means there is no left child or there is no right child. A node which has both left and right pointers null means it's a leaf. It has no children. Easy. Okay, so what can we do? We have some function which acts on a node and does some stuff. Okay, so we also have a traverse function, and it's going to check whether there is a left child. If there is a left child, then it's going to traverse starting from that left child. And it's going to do the same thing for the right child, checking, and if there is a right child, it's going to traverse. And it's also going to do some significant computation on the node itself. Significant computation means if I need to do this and there is no work to be done, then I'll again have a lot of overhead. So is this worth it? Depends on the computational weight of this guy here. Okay, and then it's quite simple. We just construct a tree, we do traverse on the root of the tree, and essentially we're done. So that's how it works sequentially, very easy. Recursion, that's it. Traverse is a recursive function. All right, can we parallelize this? Not with a for loop. So how can we do that? Well, introducing tasks. So in our main function, we're going to start a parallel region, OMP parallel, that extends here. And then we have an OMP single. So just a single thread is going to do that block of computation. And that block is the start of our recursive traversal of the tree. It's very important that that happens in a single directive. Because if we didn't do that, all the threads would start traverse at the root of the tree. And you would traverse your tree as many times as there are threads in your team. Yeah, that's not the point. I mean, then lots of work happens, but nothing interesting is going on. So basically, we have a traverse here, which is executed by only a single thread. Which one? I don't mind, I don't care, but only a single one. That's important. Okay, so a single thread is going to execute the first call to traverse. So where's the parallelism coming from? Because we want parallelism. Well, each invocation, each execution of traverse is going to generate two tasks. Well, at most two tasks. No tasks if that node is a leaf. One task if it has a single child. So at most two tasks because a node can have at most two children. And as you can see, again, we test whether there is a left child. If so, we traverse, but we create a task. So pragma OMP task will create a new task. And we do that both for the left and for the right child. Okay. So essentially that means if you go, you start from the root of the tree with a single thread, because a single thread is doing the traverse. Okay. That single thread is going to spawn two tasks. One for left, one for right. And that single thread might continue with the process P. There are other threads in the team. One of them will pick up the task of doing the right traversal. Another thread might pick up the task of doing the left traversal. each of them may potentially spawn 2 new tasks. So somewhere in the background, we don't care where it is, we don't have to manage that manually, but somewhere a queue of things to do is maintained. And as soon as a thread is bored, it gets a new task. That's sort of how it works. A lot more details to that, but we'll come to that in a minute. So this allows us to, for instance, parallelize recursive tasks. Okay, one thing you probably can already guess is that if we do this really to the end, so for the entire depth of our tree, this is not going to be very efficient, because we will create a lot of overhead with these tasks, with managing these tasks, with switching from one task to another when it's finished, etc., etc. So this is going to be an expensive operation. So that means that the processing which happens in a single task must be significant with respect to the overhead of creating it, managing it, etc., etc. So that's important. And we'll see that that task directive actually has an if clause. So we can spawn a new task if a certain condition is met, which basically means if there is sufficient work, spawn a task. Otherwise, just do it in this thread. Continue with the execution as you would without tasking. So that is a very important concept here. Okay, so we mentioned this. So there are a few things here, and that is basically that a task can be done immediately, or it can be deferred. And when you create a new task, that's such a decision point. So it might be that at a certain point in the execution, we arrive at a point in the code where a new task is spawned, but the runtime sees, okay, everyone's busy now. It really doesn't make, and my queue is pretty long. I'm not going to spawn a new task. Just keep on doing this. So the task thing is ignored in the sense that the runtime says, yeah, okay, I'm not going to do that. You are going to do your own task. I'm not going to create a new one. So that is something that the runtime can decide. And that's, of course, a good thing, because that means that it can deal with load balancing. So there are decision points when when it is decided whether a task is scheduled or deferred for later, or not scheduled but executed immediately in the existing thread as part of the existing task. We'll get into the details later. Okay, so the task directive. As usual, there are a number of things. We have default, which I already showed you. Then we have private, etc., etc. We have shared, and we have if. So the if is pretty important here because that allows you to control at runtime whether your task is going to be created or not. Boolean condition, easy. Okay. So that's quite easy. So what is the idea? So when a task hits a task construct, so a task directive, then a task is generated from that code, and it will be the structured block to which that task is associated. And then there are a few points. Either indeed the thread where the task is encountered may execute the task itself immediately, or the task may be deferred to the runtime for later execution. So suppose now that we had the situation where the computation in a node depended on the results of the children. if we are aggregating in a tree, and that is the case, then of course we need a synchronization mechanism. We need for the parent task to wait until the tasks which it spawned for its children are actually executed. And this you can do using a task wait. So that's basically here. So basically, if you have if false, whatever reason false, yeah, then of course no task is ever spawned, and that will be the same as serial, of course. So task scheduling points. So scheduling points means, is it going to be deferred? Is it going to be executed immediately? Is a scheduled task going to be executed, and so on? So one of the scheduling points is when the generating task hits a task directive. In the generated task, after the last instruction in the task region. So basically, when the task is finished, you also have a scheduling point. And then, if a task is untied, that means that it can actually be, let's say, interrupted at any given point. It may be suspended. That's what untied means. Task can be suspended. That is a clause on the task creation thing. And then at implicit and explicit barriers, as you will see later. And of course, task wait itself is a very explicit barrier for tasks. Okay, so that's essentially when you have scheduling points. And dus, so at each scheduling point, a task can start running. So that means typically an existing task is put to sleep, or it can be resumed, or it can be suspended, whatever. That is basically the idea here. Okay, so more or less clear how tasks work. A nice example of this is implement quicksort. And that means that your if for new tasks would be the length of the list. If your list is too short, don't do it in a subtask. Do it yourself. So that's basically a good example and an easy example of having an if clause on tasks. Okay, scheduling and synchronization. Implicit barriers are, of course, at the end of a parallel region. Yeah, obviously, I mean, then everything is going to disappear. So yeah, of course, there is a scheduling, there is a synchronization point. At the end of all other work sharing directives, at the end of a for, at the end of a single, etc., etc. And there is also implicit synchronization, which you can remove with no wait. If you don't require synchronization, just put a no wait, and you will gain some performance at the risk of creating race conditions, obviously. Code without no wait may be correct. Code with no wait has the potential to be incorrect. So you need to know what you're doing. There is also explicit synchronization using the critical directive. Okay, so what's critical? The unclosed code is going to be executed by one thread at a time. So basically, that means that if a thread arrives at a critical point, it will start doing that. If the next task arrives there, it will hold. So there is an explicit barrier at the beginning of a critical. So as soon as the first task or the first thread is done, then the next thread may enter. The others still wait. So this is like this thing in a supermarket, basically, where you have this thing which goes open and closes again. So it's sort of barrier. Only one person can pass, then the thing closes again. Another person can pass, thing closes again. Well, at an airport might be better. So basically, that's the idea. You can pass only one by one, and you get a queue potentially until everyone passes. So basically, you can also name critical regions because you may have nested critical regions or multiple critical regions, and that means that you can refer to them by name, which is of course important in Fortran because you have OMP critical, OMP and critical. Which end? So in C and C++, it doesn't matter because you have nesting with the structure of your code. Okay. But you can also name them, and that you can name them is useful from time to time. All right, so of course, this is serialization because only one thread can do things at a time. So if you have 100 threads, one of them is executing, all the rest is waiting. We could have done the reduction with a critical. Remember our pi thing? If we would have done pi plus equals something in a critical region, no waste condition. No performance either, but you can't have it all. Okay. So here's an example in C, C++. And this is essentially a reduction again. As you can see, we have a for. In the for loop, we increment the counter. And in this case, we don't have a reduction. Well, we don't have a reduction clause, but we solve the problem by having a critical region. Okay? This is a very bad idea. Because in each iteration, you are serializing. Because the counter is going to be incremented by each thread separately. So unless this here, whatever happens, is really, really a lot of work, this is going to be problematic. We can try it later to see the performance difference, but it will be pretty huge. Of course, we can still use a critical region efficiently. What we could do in our computation for pi is say, well, okay, I'm going to have a private variable to each thread. So that can be incremented with values for pi without any trouble. And then after that iteration, I'm actually going to aggregate all those thread private values into a shared variable, and this I'm doing in the critical region. So that means that indeed each thread is doing that. That will happen in series, but that's only once for each thread. That's very acceptable. That will generate very little overhead. If I would have the critical region within my for loop, then I will generate significant overhead. We'll have a look at the difference. So this is the same thing for Fortran. Not really any surprises here. Okay. Another example in Fortran. So this would actually be the same thing. It's also a reduction, but now the reduction is essentially a maximum reduction rather than a sum reduction. Same thing, but different. Okay. That's likely the same thing. Yes, that's the same thing for C++. Whatever. Okay. Is this more or less clear? So critical regions can be useful, but to be used with a lot of care. All right. Next, nesting and binding. So Then we have to talk about extent, static extent and dynamic extent. And that has to do with nesting and where a certain directive belongs. As I already mentioned, you can't really have a work sharing directive outside of the scope of a parallel region. Doesn't make sense. So does that mean that if you have a function that where you would want to use a work sharing directive, for instance, a for, that you would have to open a parallel region, do your for, close your parallel region in that function? Not necessarily. So if you were to write your code that way, then of course the work share directive would be in the static extent of your parallel region. Okay. But of course I can also open my parallel and then call my function. So statically, indeed, the work share directive is not in the parallel region, in the static extent of my parallel region, because it's a total different part of my source code. But dynamically, it's of course in the extent. So that's a little bit the difference. And that is illustrated graphically here. So we have Fortran example, but it doesn't really matter. So we have two subroutines, B and C, and they're called within the context of a parallel region. And then there is another call to a subroutine in the, well, outside of the parallel region. Okay, so call B, call C in Fortran is similar to doing a function call in C or C++. All right, so here's the example. Here's the subroutine B. So we have an OMP parallel in our program. So that's like our main function in C. And then in our subroutine, we just have an OMP do. So since I'm calling B from within a parallel region, that's perfectly fine. So basically, the static extent of my parallel region is simply these two lines of code. The dynamic extent, on the other hand, is everything that's called within that parallel region as well. So basically, our do is in the dynamic extent of our parallel region, no problem. So it may look, if you look at the source code, as if that OMP do is orphaned, in the sense that there doesn't seem to be an unclosing parallel, OMP parallel, but of course dynamically there is one. So as long as this is okay, it's all fine. Okay. So if you were to call it from outside of a parallel region, then of course you would have an orphaned directive. All right, so this is a bit of summary. We have parallel, we have section. So the work sharing directive sections for do, work share only in Fortran, and single. And then for tasking, we have task. For synchronization, we have, then we have some combined things, parallel for, parallel do, parallel work share only in Fortran. And then we have synchronization construct critical, and in a way also task wait, which is not listed here, but it is also a synchronization thing, of course. Okay, so let's break for lunch and do the exercise later because it's 1:30 and you might be hungry. So I hope there are sandwiches. There ought to be, but who knows? Let's have a break. Shall we say 1:15? That gives us 3/4 of an hour. That's probably enough. Everyone agrees? No objections? Okay. I'll stop sharing. I'll also stop the recording in order not to make it infinitely long. Oh, I've missed a lot of things in the chat. Why don't I get a beep in the when the chat is doing something? That is very annoying. Okay. All right. So let's see here. Okay, so all right, that was easy. All right, I'll stop sharing and stop recording. And please remind me to